Hello and welcome to my class. In this video, I'll be showing you that if a random variable x is binomially distributed with parameters n and p, with n standing for the number of trials and p standing for the probability of success, then one can obtain the variance of x. The first thing you must note from my previous video on getting the expectation of x for a binomial distribution is that expectation of x is equal to np. Also, if x is binomially distributed, please take note that you must recall f of x will be equal to n combination x, p raised to power x, q raised to power n minus x, where q is the probability of failure and p is the probability of success. Now, that being said, note that variance of x is equal to expectation of x squared minus expectation of x all squared, and we shall be using this to get the problem solved. So variance of x equals this implies that we would have expectation of x squared minus what expectation of x is, np all squared, and this will give us expectation of x squared minus n squared p squared. So hold on to that. Next, we're going to say but expectation of x squared can be re-expressed as expectation of x minus 1 plus x, and this would mean having expectation of x minus 1 plus expectation of x. This is simply because it is easier to go about the problem of getting the expectation of x squared in this manner than getting the expectation of x squared using x squared directly. Now, we have done nothing wrong, because if you multiply x by x, you end up having x squared. Multiply x by 1, you end up having minus x, then plus the x over here would give you this, and this will reduce to x squared. So we've just written x squared in another form. Now, going by that, we would now have expectation of x squared to be equal to expectation of x minus 1, like we wrote earlier on, plus expectation of x, which is np already. So the problem again reduces to getting expectation of x minus 1, and this will be equal to summation from x equals to, because we have x and x minus 1 here, so n combination x, that is x minus 1, which takes the place of the random variable now, times n combination x, p raised to power x, q raised to power n minus x. Now, the next thing we are going to do will be to expand and simplify. So this will be x equals to n x minus 1, and I'm going to expand n combination x to give us n factorial n minus x factorial x factorial, and then this will be p raised to power x, q raised to power n minus x, of course. Next, I'm going to do this x equals to n x minus 1. Then I'm going to expand this to get n minus 1 n minus 2 factorial. You can now see why I'm starting my iteration at 2 and terminating at n. Then this will be n minus x retained, x minus 1 x minus 2 factorial. Okay, and then I'm going to write this as p raised to power 2 times p raised to power x minus 2, which, of course, when you simplify by indices, gives you p raised to power x. And this will be q raised to power n minus x brought here. Okay, now, obviously, one can cancel x and x minus 1, and I can bring out the constants n minus 1, and then p squared. and this will leave me with summation from x equals to n, and this will leave me with n minus 2 factorial all over n minus x factorial, good, x minus 2 factorial, and times p raised to power x minus 2 q raised to power n minus x. Now, please take note that this is a distribution, and like I told you previously, distributions satisfy the following. If f of x is a distribution, it must be positive, okay? And 2, the summation of a distribution gives 1. So these two properties must be satisfied, and I can tell you for a fact that this is a distribution. So summing this distribution over the domain will give us 1. So we end up having our result for that as n minus 1 p squared. Okay, so the next thing we will do will be to incorporate our results into the variance of x. So variance of x now becomes expectation of x squared, which is now n minus 1 times p squared plus np. So this is expectation of x squared, take note, and we've gotten this, okay? So be n minus 1 p squared plus this np over here, I'm going to bring it here, then minus n squared p squared. Okay, so the next will be to expand n minus 1 p squared when expanded will give you n squared p squared. Okay, when n multiplies this and then multiplies p squared, when n multiplies minus 1 and then multiplies p squared, you end up having minus np squared, then bring in np and bring in minus n squared p squared. Okay, so this cancels this, and we are left with np minus np squared. So we have variance of x to be np minus np squared, which we can simplify further to be np, which is common, into bracket 1 minus p, and 1 minus p, guys, is q. So 1 minus p is q, so this will be npq. So we have the variance of x to be npq if x is binomially distributed. So this completes the proof. Thank you very much for watching this video. Do like, share, and subscribe to my YouTube channel, GER Hub on YouTube, okay, for more videos like this, or follow my Facebook page, John Hussein. Until some other time, stay blessed.